Some applications of stationary points involve maximizing or minimizing something. For example, a business would want to make profits as large as possible. On the other hand, a car designer would want to ensure that wind resistance is as small as possible. Let us consider the first example. Suppose we have a piece of wire 40 centimeters long. If we want to make a rectangle from the wire, how should the length and breadth be chosen in order to give the greatest possible area? Consider the following possible dimensions. If we take the length to be 15 centimeters and a width of 5 centimeters, this would give a perimeter of 40 centimeters and an area of 75 centimeters squared. On the other hand, if we take the length to be 9 centimeters and the width to be 12 centimeters, this would still give a perimeter of 40 centimeters. However, the area increases to 96 centimeters squared. In order to avoid this trial and error process to find the maximum area, we can use differentiation. Let the breadth be x centimeters, the length be y, and the area a centimeters squared. There are two quantities, one being the fixed perimeter and the other the varying area. We can express these as equations in terms of x and y. The fixed perimeter may be expressed as 2x plus 2y equals 40, while the area xy equal to a. Our aim is to express the quantity that is varying, that is, the area, in terms of only one variable. In order to do this, we need to make the other variable subject of the fixed equation. Therefore, making y subject of the formula in equation 1, that is, 2x plus 2y equals 40, this gives y equal 20 minus x. If we then substitute this in the second equation, we obtain a equals 20x minus x squared. We have therefore expressed the varying quantity in terms of just one variable. In order to find the maximum area, we need to differentiate our expression for a with respect to x and equate the result to 0, since the gradient at a stationary point, that is, a maximum or minimum point, is 0. Therefore, dA by dx is equal to 20 minus 2x, which is equal to 0, from which we can conclude that x equals 10 centimeters. We must now show that this value of x does give a maximum. Recall, if the second derivative is greater than 0, then we have a minimum, while if the second derivative is less than 0, then we have a maximum. Differentiating again therefore gives d2a by dx squared is equal to minus 2, which is less than 0. Therefore, we have a maximum. Substituting the value of x, we obtain the value of y, which turns out to be 10 centimeters. Therefore, the maximum area is enclosed by a square of sides 10 centimeters by 10 centimeters, giving an area of 100 centimeters squared. Moving on to another example, determine the area of the largest piece of rectangular ground that can be enclosed by 100 meters of fencing if part of an existing straight wall is used as one side. If the breadth is taken to be x and the length y, then area may be expressed as A equals xy. The perimeter P of the rectangular ground is given by 2x plus y equals 100. Making y subject, y equals 100 minus 2x. Therefore, the area is equal to 100x minus 2x squared. And the first derivative, dA by dx, is equal to 100 minus 4x, which is equal to 0 for a stationary point. Therefore, x is equal to 25 meters. We need to obtain the second derivative to confirm that this value of x gives a maximum. Since the first derivative was equal to 100 minus 4x, we obtain a second derivative of minus 4, which is less than 0, implying we have a maximum. Obtaining the corresponding value of y, since 2x plus y is equal to 100, and we substitute the value of x, we obtain y is equal to 50 meters. Therefore, we have a maximum area of 1,250 meters squared. Let us consider a final example. A cylindrical tank closed at each end holds 100 cubic meters of lubricating oil. Determine the dimensions of the tank so that the surface area is a minimum. The surface area of a closed cylinder is given by 2 pi r squared plus 2 pi r h, where r is the radius and h the height, while the volume V is given by pi r squared h, which is equal to 100. Therefore, making h subject, we obtain h equals 100 all over pi r squared. If we substitute the value for h in the first equation, we obtain an equation for the surface area in terms of r only. We therefore have surface area is equal to 2 pi r squared plus 200 r to the minus 1. If we differentiate once, we obtain 4 pi r minus 200 r to the minus 2, which we can equate to 0 for stationary points. Making r subject, we have r is equal to 2.5 meters. By obtaining the second derivative and substituting the value of r, we confirm that this value of r does in fact give a minimum surface area. The second derivative is 4 pi plus 400 r to the minus 3, which is greater than 0 when r is 2.5. By substituting r into the equation, we obtain the corresponding value of h, which is equal to 5.1 meters. Therefore, we obtain a surface area of 119.4 meters squared.
We hope you have found this presentation useful. Thank you for viewing. Goodbye.